French chemist Le Chatelier explained, when a system at equilibrium is subjected to stress, the concentration will shift to reduce the stress. Le Chatelier's principle helps us predict in which direction a reaction will shift when subjected to a stress like heat. At equilibrium, when the temperature of a system is raised by adding heat, the system will shift in the direction that enables it to absorb heat. Conversely, when heat is removed from the system, the equilibrium will shift in the direction that produces heat. Le Chatelier's principle also predicts how a system will react to a change in the concentration of one of the participants in the reaction. If stress occurs by adding too much reactant, it seems logical that the system will respond by creating more products to use up the additional reactants. Or, if a reactant is removed from the equilibrium, we would expect that products will decompose to counteract the stress in order to produce more of the removed participant. Visual evidence in the laboratory confirms that equilibrium systems act in this manner. In solution, a reaction between light yellow ferric ions and colorless thiocyanate ions produce a distinctly deep red ion, an iron thiocyanate complex. The equilibrium expression is this. Now, a source of only one of the reactant ions, the thiocyanate ion, is added in the form of crystals of ammonia thiocyanate. The color of the solution deepens. What's happened? The increased concentration of thiocyanate ions reacts with ferric ions to produce more of the iron thiocyanate complex until a new equilibrium is established. Le Chatelier's principle seems to be a practical idea, but how does it mesh with our collision model for chemical reactions? Consider events at a hydrogen iodide dance. Things have reached equilibrium. A few couples, a few singles. Every now and then, a lonely iodine meets a lonely hydrogen, and couples form. But in another corner, two couples meet and fight, leaving a pair of lonely element molecules again. Suddenly, a bus arrives, loaded with one kind of molecule, hydrogen. Every lonely iodine is in heaven. The chances of a meaningful encounter have gone up enormously. Momentarily, equilibrium shifts to produce more product couples. But this creates more couples who get into fights and decompose into individual elements, until finally things settle down to a new equilibrium with more couples. Such a collision model, even without the dance floor embellishments, is a comforting support to Le Chatelier's principle. Although it's a comfort to be able to predict how reactions change directions, chemists are really happy when they can quantify an expression. And they're not the only ones. Before a chemical plant can be built, engineers require accurate data to design the facilities which control large-scale operations. Bankers must be certain that a plant will yield a profit. The good news, there's a mathematical expression for Le Chatelier's principle. And even better news for those who hate math. The calculations are dead simple. Laboratory experiments reveal a fixed value for the ratio between reactants and products at equilibrium. Measure the equilibrium results in moles per liter of 3 experiments under the same conditions. Looks like a mess of numbers, doesn't it? We'll see if we can find something constant. Let's try this ratio. Try it with each experiment. Alas, nothing very encouraging about these ratios. But wait a second. Go back to the original equation. We've left something behind. There were 2 moles over here. We could write the equation like this. Let's redo our ratio, but using a value for each mole of reactant. This part of the expression can also be represented this way. The product raised to the power of the number of moles in the reaction. Now calculate this value for each experiment. Close enough to a constant value, just what we were looking for. This constant is called the equilibrium constant. At 423 degrees Celsius, the equilibrium constant of hydrogen iodide is this. Knowing this constant allows us to shift to huge volumes in an industrial setting to predict mathematically the yield of a reaction at 423 degrees Celsius. From the results of many equilibrium experiments, a general equation can be written. This many moles of substance A react with this many moles of substance B to produce this many moles of substance C and this many moles of substance D. The law of chemical equilibrium is an elegant way of expressing this concept. For this general reaction, the equilibrium constant is calculated like this. Reconsider a hydrogen iodide reaction. An ammonia reaction looks like this. Since convention places the products on the top and the reactants on the bottom, we can estimate the behavior of a reaction at a given temperature with just a quick glance at the equilibrium constant. A very small constant means only a little product of equilibrium compared to the reactants. A constant with a value about 1 means equilibrium will produce a roughly equal balance between products and reactants. And a very large constant will result in a great deal of product and only little reactant at equilibrium. The equilibrium constant is a powerful and practical working tool for chemists. In the next program, we will see how one man and his understanding of chemical equilibrium changed the course of history in this century.